EDX Core Pure, Matrices 3, Determinants and Inverses, Inverses and Transformations. Multiplying by an inverse matrix may be viewed as matrix division, in the sense that we are looking for a matrix which is reversing the effect or undoing the transformation produced by multiplying by the original 2 by 2 matrix. For example, a point P is mapped to the point given Q under the transformation represented by the given A. Can we find the coordinates of P? Well, we know that if we multiply A by the point P, which I'm going to call xy, we'll get the image, which in this case is 4 minus 2. If I now pre-multiply both sides by the inverse of A, we'll get the identity matrix times xy. So I've got to pre-multiply the right hand side by the inverse of A, which would be a 10th 3, 1, minus 4, 2 times the image 4 minus 2. So that gives us xy is 1 minus 2. So by multiplying the image by the inverse of A, we've been able to work backwards and find the coordinates of the object P. An important property of inverse matrices is that if you multiply a matrix by its inverse, you will always get the identity matrix. For some simple transformation matrices, such as reflections, rotations, enlargements and shears, you may be able to work out what the inverse matrix is by considering what the reverse transformation would need to be. However, if you're not sure, or the transformation is a little bit more complicated, then you can always find the inverse matrix using the rule that we've looked at in previous presentations. So if we consider a few transformations first, and feel free to pause the video at any point to have a think about the answer as we're going along. So here we have a matrix T which is a reflection in the x-axis, and we are looking for the inverse matrix. So if T has reflected an object in the x-axis, then to get back to the original object, the inverse of T must be another reflection in the x-axis. So this is an example of what's called a self-inverse. The inverse of T is the same as T. It's worth noting that the determinant of this particular transformation is minus 1. So the object and the image would have a change in the orientation of the vertices, for example. Here we have a transformation T, which is reflection in the line y equals x. And again, to get back to the original, to undo the effect of this matrix and back to the original, the inverse matrix would need to be another reflection in the line y equals x. And again, the determinant of this matrix is minus 1, so this would be a change in the orientation of the vertices. In both cases, the area would be the same, but the orientation of the vertices would alter. So here now T represents a 90-degree rotation anti-clockwise about the origin. So that's a rotation of plus 90 degrees. If we want to find the inverse matrix, then we'd need to find a 90-degree rotation clockwise about the origin. So that's called a rotation of minus 90 degrees. And if we substituted the angle in our rotation matrix with minus 90, remembering that cos of minus 90 would be 0 and the sine of minus 90 would be minus 1, the inverse matrix in this case would be 0, 1, minus 1, 0. And the determinant of the original matrix was 1, and the determinant of this inverse matrix is also 1. So there is the orientation of the vertices is exactly the same, and the area of the object and the image would be exactly the same. Now here we have a matrix which is representing a 180 degree rotation about the origin. So the inverse matrix, so the matrix that will do the opposite of that, needs to be another 180 degree rotation about the origin. So the inverse matrix would again be -1, 0, 0, -1. The determinant of t is 1, and therefore the orientation of the letters will be exactly the same on the object and the image, and the area of the object and the image would be the same as well. It's worth noting here that clockwise rotations are considered to be negative rotations. So here, in this case, t represents a horizontal stretch by scale factor k. So to create the inverse matrix, we need to do the opposite. We need to undo that horizontal stretch. If you look at the determinant of t, the determinant is k, so that means that the area will be k times bigger. So to go from the image back to the object, we need a determinant that would be 1 over k. So to undo this horizontal stretch, our matrix, our inverse matrix, is going to be 1 over k, 0, 0, 1. And its determinant, as you can see, is 1 over k. So notice the determinant is k squared. So we need an inverse matrix whose determinant is 1 over k squared to undo the effect of t. So the matrix that will undo that would be 1 over k, 0, 0, 1 over k. And you can see the determinant of this matrix is 1 over k squared. This is an example of a shear where the x-axis is invariant, so it's parallel to the x-axis, and the interesting thing about t is that its determinant is 1, so the area of the image will be the same as the area of the object. So we need a matrix whose determinant is 1 but has the opposite effect, or will undo the effect of t, and the matrix that will undo that is 1 minus k, 0, 1. And again, the determinant of this inverse matrix is 1. So the object and the image will have the same area. In an earlier video, we looked at the inverse of a product of matrices, and we noted that the inverse of AB is the inverse of B times the inverse of A. Now we need to think about this as a successive pair of transformations. For example, if we apply a rotation matrix B followed by a reflection matrix A, then to undo those two transformations, we would have to undo the reflection matrix A first, followed by the rotation matrix B. So that would be B minus 1 times A minus 1. The following simple transformations are applied in 3D, and the things that we've looked at in the past, we've looked at a reflection in one of the planes, z equals 0, which is the xy plane, y equals 0, which is the xz plane, and x equals 0, which is the yz plane. So in this case, the matrix that does, for example, reflect in the z equals 0 plane, to get back to the original object, the inverse matrix would need another reflection in that plane. So the inverse matrix would be the same as the matrix M. So that's another example of a self-inverse matrix. If we think about rotations of multiple of 90 degrees about one of the axes, then the inverse matrix would do multiples of minus 90 degrees about the same axis in order to undo the effect of the rotation. Here we can see a matrix M which has reflected the red object in the ZY plane to create the green image, and this is the matrix that has achieved that. It's worth noting that the determinant of M would be minus 1. So the volume of the image and the object must be the same, but the orientation of the letters will be changed. The inverse matrix M minus 1 will reverse this transformation and take us back to where we started. So in order to reflect the green object back to where it came from, the red one, we would need another reflection in the YZ plane. So here the inverse matrix would be exactly the same as the matrix we can see. The inverse of M would be M itself, another example of a self-inverse. So that brings us to the end of matrices 3, determinants and inverses.